Dear students, this is Kani's method. This is syllabus Kani's method of analysis applied to continuous beams and single bay, single story rigid frames without sway and with sway. The Kani's method is developed by Caspar Kani. This method is an excellent extension of the slope deflection method. Like moment distribution, it is a method of solving slope deflection equation by an iterative method. It is one of the most convenient methods for the analysis of multi-storied frames. This is the advantages of Kani's method. All the computations are carried out in a single line diagram of the structure. The second one, the effect of the joint rotation and sway are considered in each cycle of iteration. And this method is thus becomes very effective and easy to use, especially in the case of multi-storied building frames. The most significant feature of the Kani's method is that the process is self-correcting. And the fourth one is convergence is generally fast. It leads to the solution in just a few cycles of iterations. And the fifth one is the Hardy-Cross method distribution only the unbalanced moments at the joints, whereas the Kani's method distributes the total joint moment at any stage of iteration. And the next case, in the slope deflection method, rotations and displacement of the joints are treated as unknowns. And the simultaneous solution of the various slope deflection equation along with the equilibrium equation give the values of the unknowns. In many cases, especially in the case of frames, the solution becomes very clumsy. In the case of moment distribution also, solving the above mentioned equation is numerically without explicitly writing them by using the Gauss iteration. The quantities iterated in the moment distribution methods are increments to the member and moments instead of the end moment themselves. The difference between the Kani's method and the moment distribution method is that the Kani's method iterates the member and moments themselves rather than iterating their increments. But the Kani's method essentially consists of a single simple numerical operations performed repeatedly at the joints of a structure in a chosen sequence. These are the sign conventions. Clockwise end moments and the clockwise end rotations are taken as positive, and anti-clockwise moments and anti-clockwise rotations as taken as negative. Let AB represents one of the spans of a framed or continuous structure. Let the span carrying an external loading. Let the ends A and B undergo rotations theta A and theta B respectively as shown in this figure. Let us assume that the lateral displacement of the ends does not occur. Let MAB and MBA represent the end moments for the span AB. These moments are determined by the following steps. The step 1. The end A and B of the member are firstly considered as fixed. Corresponding to this condition, the fixed end moments M bar AB at A and M bar BA at B are determined. The second one, now maintaining the fixity of the end B, and the end A is rotated through an angle theta A by the application of a moment 2MAB. At A, for this condition, a moment of MAB is induced at the end B. The moment MAB, that is called the rotation contribution of the end A. And in the third stage, the end A is considered as fixed and the end B is rotated through an angle theta B by the application of a moment 2MBA at B. For this condition, a moment of MBA is induced at the end A. This MBA is called the rotation contribution of the end B. Therefore, the final moments MAB and MBA can be expressed as MAB is equal to M bar AB plus 2MAB plus MBA, and MBA is equal to M bar BA plus 2MBA plus MAB. In the right hand side, MAB and MBA are the rotation contributions. For the moments AB, when we refer the final moment MAB at A, the end A may be referred to as the near end and the end B is referred to as the far end. Parallelly, when we refer to the final moments MBA at B, the end B may be referred as near end and M and A as the far end. The moments at the near end of a member is equal to sum of the fixed end moment at the near end due to the loading on the member and twice the rotation of the contribution of the near end and the rotation contribution of the far end. For example, MAB is equal to fixed end moment, that means M bar AB plus twice the rotation of the near end, that means plus 2 MAB, and rotation contribution of the far end, that means plus MBA. Also, these rotation contributions can be calculated by minus half of KAB by sigma KAB into sigma M bar AB plus sigma MBA. That means this ratio is called the rotation factor for the member AB at the joint A. Generally, it can be written as sum of the rotation factors of different members meeting at a joint along with the sum of the far end contribution of the members meeting at that joints are known, then the near end moment contribution can be determined. When the far end contributions are not known, they can be assumed to be 0. This equation can be generally written as the rotation contribution is equal to the rotation factor into the sum of the fixed end moments of that particular joint plus the sum of the rotation contribution of the far end. This is the procedure for the Kani's method. The step 1. Calculate the fixed end moments in all the members of the structure. Find the resultant restraint moments at each joint and enter this value of the resultant restraint moment within a square made at each joint. Like this. This is the set square. Calculate the rotation stiffness K values and rotation factors for the members meeting at the joint. These values are entered outside the first square, but inside values are entered outside the first square but inside the second square. That means here inside the second square and outside the first square. That means rotation contribution factor will be entered at here. And the third one, compute the rotation contribution of the two ends of all the members by the Gauss-Seidel iteration performed at all joints starting with the approximation that now continue the iteration through the several cycles till the practically the same values we obtain in two successive cycles. Now repeating the procedure, and the final moments can be found out by using this equation. This equation generally can be written as the final moments is equal to the fixed end moment of that particular point plus 2 into the rotation contribution of that near end plus MBA means the rotation contribution of the far end. Then we can discuss an example. So determine the support moment A, B, C and D for the continuous beam shown in figure. In the first step, you have to calculate the fixed end moments M bar AB, M bar BA, M bar BC, M bar CB and M bar CD and M bar DC. In the next step, you have to calculate the rotation factor. The rotation factor means it's the minus half of the distribution factor. That means you have to find out the relative stiffness and the total relative stiffness and the minus half of KAB divided by sigma KAB. This KAB divided by sigma KAB will be the distribution factor and into minus half will give the rotation factor. Then we have to enter into the Kani's table. The values have to be entered in the Kani's table like all the fixed end moments have to be entered above the horizontal line and the sum of the fixed end moments at this particular joint will be entered in this square and the rotation factor will be entered like this. This is the Kani's table. Then the rotation contribution at the fixed end that will be equal to 0. That means the rotation contribution at A and D that is equal to 0. Then the next step we have to find out the rotation contribution at BA, BC, CB and CD. Then how will you get the rotation contribution at BA? The rotation contribution at BA will be obtained as it is the sum of the total fixed end moments at here plus the rotation contribution of the far end, that means AB and CB, that means minus 77.37 plus 0 plus 0. That value into minus 1 by 6 will be the rotation contribution of BA, and that value into minus 1 by 3 will be the rotation contribution of BC. This is the rotation contribution of BA and BC. In the next step, we have to find out the rotation contribution at the end CB and CD. That means the sum of the fixed end moment at here plus the rotation contribution of the far end, that means 25.79 plus 0, then we will get a value. Minus 1 by 4th of that value will be here and minus 1 by 4th of that value will be here. These are the values. And we have to continue this iteration. That means minus 7 in the next cycle. That means the minus 77.37 plus the far end contribution is 0 plus minus 23.74. Then we will get a value. Minus 1 by 6 of that value will be here and minus 1 by 3 of that value will be here. Similarly, in the second cycle for CB, that means minus 69.17 plus 33.7 plus 0 into minus 1 by 4 will be here and into minus 1 by 4 will be here. We have to repeat this cycle till the value of the two successive cycles will be is equal to 0. If the value of this cycle will be same as in the previous cycle, then we can stop the iteration. After that, we can find out the final moments by using the equation for MAB, the fixed end moments plus 2 into rotation contribution plus far end contribution. That means minus 17.58 plus 2 into 0 plus 17.21 will be the MAB. And MBA means the fixed end moments plus 2 into this value plus far end contribution. That will give the MBA. After getting the final moments, we can draw the SFD and BMD. Then we can move to the next problem, analyze the given beam by using the Kani's method. The difference between this problem and the previous problem is that the far end is a simply supported one. That means after getting the fixed end moments and the rotation factor, then we have to enter all these values into the moment distribution table. That means we have to enter the fixed moments in the above horizontal line and we have to enter the rotation factor. Then if the end supports are the simply supported, as in the case of the moment distribution method, if the end supports are the simply supported, that means the total moment, the moment at that particular joint will be is equal to 0. If the moment at that particular joint is not equal to 0, we have to make that moment is equal to 0 first. That means in this case, we got this value as 10. That means we have to make this 10 is equal to 0. So that means we have to apply minus 10 here. When you apply minus 10 here, the half of the moment will go as a carryover to the far end. That means minus 5. After this carryover, please find out the sum. Then we will get minus 25 here. Then the sum of the fixed end moments we have to enter in this table is 40 minus this value. That will be the value you have to enter here. After that, we can continue the Kani's method. Then after getting the rotation contribution, we can find out the final end moments. In this case, it is an overhanging portion. In the case of an overhanging portion, we have to find out the fixed end moment and the rotation factor, and we have to enter all these values here. If there is any overhanging portion, find out that overhanging moment. That means 15 into 0.6, that value is 9. 15 into 0.6, that is in the clockwise direction. That means MDE will be minus 9. we have to enter minus 9 here. In order to make the total moment at this joint will be is equal to 0, we have to apply plus 9 here and the carryover will be 4.5. That is the first step. We have to find out the overhanging moment and have to enter the minus value here. And now to make the total moment is equal to 0, we have to enter the plus value here and the carryover will be here. After considering the overhanging moment, please treat this joint as a simply supported one. That means we have to make this moment also is equal to 0. This 13.33. In order to make this 13.33 is equal to 0, we have to apply minus 13.33 here. So minus 6.67 will be the carryover. After these two steps, that means in order to, after making the moment, overhanging moment is equal to 0 and the moment at the joint D is equal to 0 and the carryover, we have to add the moments. After adding, we will be get like this. After getting this value plus the fixed end moment value will give the value which you have to enter here. After entering this value, then we can find out the rotation contribution, and after getting the rotation contribution, we can find the final end moments. This is a support settlement. As in the case of moment distribution method, if there is any support settlement, there should be some additional